In this lecture video, we'll discuss about vector spaces. By the end of this discussion, you should be able to define a vector space and recognize some important vector spaces. Show that a given set is not a vector space. Let V be a non-empty set of objects on which the operations addition and scalar multiplication are defined. V is a vector space if and only if all vectors in V satisfy all the axioms listed with C and D that are real numbers. Okay, we have the 10 axioms that will characterize a vector space. U plus V is in V. This is closure under addition, meaning to say if you are going to add two real numbers, the result should be a real number as well. If you are going to add, let's say, a 1 by 2 matrix, the result should be a 1 by 2 matrix as well. So that is the meaning of closure under addition. The sum must belong to the same vector space. Next, U plus V is equal to V plus U. Meaning to say, the order of addition must not matter. So that is the commutative property of addition. Next, we have the associative property of addition. These must be satisfied. And then fourth, there is a zero vector in V such that vector U plus the zero vector is equal to U. Okay, always remember the fourth one. There should be a zero vector in the vector space. Fifth, for each vector U in V, there is a vector negative U such that when we add them, U plus negative U, the resulting should be the vector, zero vector. This one is the additive inverse. Sixth, is closure under scalar multiplication. C times U is in V. Next, we have the distributive property. We have two distributive property here. C times the quantity vectors U plus V is equal to CU plus CV. And the other one, we have the quantity C plus D times vector U. The result is C times U plus D times U. Next, we have the associative property. We have C times DU. This should be equal to C times D times U. Always remember that C and D here, the ones that are not bold, are real numbers, okay? And then next, we have the scalar identity. 1 times the vector U is equal to the vector times 1 equals the vector itself. The ones highlighted are the top of the criteria. Meaning to say, we can skip the other axioms if we have already satisfied this. Also this one. The fifth one is also important. From the previous definition, a vector space consists of a set of vectors, a set of real valued scalars, vector addition, and scalar multiplication. Alright, to show that a set is a vector space, check the following among the 10 axioms. Let's do this. But before that, let us have a quick recall on the set of real numbers. Okay, we start from the complex set. The complex set involves the real numbers and the imaginary numbers. A plus bi, where b is not equal to 0. Those are the imaginary numbers. Inside the complex set, we have the real set. Okay, dr. Inside it, we have the set of rational numbers, Q, and irrational numbers. Inside the set of rational numbers, there are integers and non-integers. Non-integers include fractions and non-terminating decimals with pattern. Meaning to say, numbers with repeating decimals with pattern can be written as fraction. Next, we have the set of integers. Inside the integer set, you have the positive integer, negative integers, and the set containing 0. Let's have the following examples. Verify whether the following set is a vector space or not on over R or the specific given set. Okay, we have the following strategy. We may prove formally using proof methods, arbitrary objects, or we can also prove informally using specific objects, disprove using counterexamples, or specific objects. So it depends on you on how you will prove this. Let's have the first, the set R. Okay, we have the closure under addition. Let's say let U and V be an element of R. Okay, let us take U plus V addition will still be in R, right? So any real number that is added to another is still a real number. Next, closure under scalar multiplication. C times vector U. Suppose that we have here 5 times vector containing 3. Okay, take C equals 5, vector U equals the vector containing 3. The answer is 15, correct? This is still a real number based on the properties of real numbers as well. Third, there is a 0 in the set. This is correct. There is a 0 vector. Recall from algebra, we have a 0 in the real set. It is in the beginning, right? Fourth, the additive inverse of each element exists. This is true because if we have here vector U that contains 3, the negative of that will just be negative 3. So it is also in the same set. Next, we have here the Z. Let us verify whether the set of integers is a vector space or not. Alright, so let's start with addition. Okay, take U. So this one is an integer, right? And then V. Let us take any integer. Negative 3. Alright. U plus V. This becomes, we have 5 plus negative 3. Adding them yields positive 2, which is an integer. So therefore, we have satisfied the closure under addition. Because the result is also a 1-by-1 matrix here. Okay, written in that form of a vector. And the answer, the result is an integer as well. Second, closure under scalar multiplication. Let's have C times vector U. Take note that C here is any real number, meaning to say it may assume a number that has decimal or it may assume fractional numbers. Take note that in proving vector spaces, it's best to use your intuition that is intended to, disprove that this is not a vector space. So let us choose a number that will disprove that this is a vector space. Take note that if we multiply 3 over 4 to 5, the result will be 15 over 4, which is no longer an element of the integer set. Okay, let us take C to be 3 over 4. So, we have 3 over 4 times 5. The result will be 15 over 4. This is no longer in the integer set. So, the scalar multiplication fails. Okay? If one of the conditions or axioms fails, then the given set is not a vector space. Always remember that all of the axioms must be satisfied. If one of them will not be satisfied, then the set is not a vector space. Next, let's have the set R star. This is the set of non-zero real numbers. We can just state it since the zero vector is not an element of R star, then R star is not a vector space. Next, let's have the rational number set. We have here the closure under addition. Closure under addition is obvious that it is satisfied. Let us try to see whether which of these can disprove this. Okay, when we say rational, it can be a fraction. Let's say 5/4. Even whole numbers are rational, okay? So that's why in the rational set, integers are inside the rational set. Okay, for the scalar multiplication, let us take C to be an irrational number. Let's say pi. Pi is irrational, okay? And let's have here vector u. Let's say vector u contains positive 5. Okay, so therefore c times vector u is equal to 5 pi. Okay, 5 pi is no longer rational. So Q is not a vector space. Next, let's have here the following. The set containing the vector x, y, z in R3 such that x squared plus y squared plus z squared equals 1. Okay, here you can see that there is an equation relating the three components of the vector. You can definitely see that there is no zero in the given set. Take note that 0, 0, 0 implies that 0 squared plus 0 squared plus 0 squared equals 1. A contradiction. 0 is equal to 1. This is a contradiction because 0 is not equal to positive 1. So here, we can skip the closure under addition, multiplication, and the additive inverse as well as the other 6 and just proceed with this one. The third, there is a zero vector in the set. This one is violated. Since there is no zero vector in the set, then it is not a vector space. Next, let's have a set of all 2x3 matrices. The symbol for this one is script M 2x3. Let's say vector U 2x3. Okay, we can put subscript on it. Let's say A 2x3, 2 rows, 3 columns. Such that all of these are real, okay? And then vector V. Let's say X, Y, Z. X, Y, Z. We can take this. Okay, let. For the addition, the addition will be, we can already drop the subscript here. The addition will be a plus x okay, as you can see, the result is still a 2 by 3 matrix. So, it is closed under addition. Next, let's have the scalar multiplication. Take C be equal to 1/2. Okay, thus, C times the vector U is equal to, okay, 1/2 A, 1/2 B, this is still an element of the set of all 2 by 3 matrices. And aside from that, all of the values here are also real. Okay? Next, what else? The third one. There is a 0 vector in the set. This is satisfied because we have the 0 matrix. 0 matrix 2 by 3. This is 0, 0, 0, 0, 0, 0. Fourth, there is the additive inverse of each element exists. So this is also true. Because if you take the negative of vector u, you will have negative a, negative b, and so on. Thus, the 6 other axioms may be proven or not. This is already obvious. Thus, the set of matrices, 2 by 3 matrices, is a vector space. Next, let's have the set of polynomials with degree exactly 2 and with degree equal or less than 2. Take note that these are different from each other. Okay, when we say a set of polynomials with degree exactly 2, the highest powered variable will be x squared all the time. For number 8, it may or may not be all the time. Okay, for number 7, we are going to verify that this is not closed under addition. Why? Because if we are going to have, let's say, you have 1 plus x squared, and then v, 1 minus x squared. Take note that these are not vectors, okay? These are just elements. Okay, 1 plus x squared and 1 minus x squared for v. If we add them, u plus v, this will result to 2, right? Because x squared plus negative x squared is 0. So, 2 is not a polynomial of degree 2. So, this one is not a vector space. Next, suppose that here on the 8th item, we also use the same u and v. By the way, the notation for the set of polynomials with degree equal or less than 2 is script P2. Alright, if we take the same values, u and v, take note that these are not vectors, okay? Just elements. Just to see whether the closure under addition will be true. So, this one, 2 is an element of the given set. So, the addition is satisfied. For the closure under scalar multiplication, it is also satisfied because whatever you multiply to a polynomial will result to the same polynomial of the same degree, just with different coefficients. Third, there is a 0 in the set. This is correct because we have the 0 polynomial. And the additive inverse of each element exists. This is also true because we can get the negative counterpart of this one. That will be negative 1 minus x squared, which is still a polynomial. You are highly encouraged to answer the following exercise for you to practice. The correct answer of this one will be shown at the end of this lecture video.